and we want to know what is the capacitance of this parallel plate capacitor. Well, what we do is we say, okay, well, we want to figure out if I put so much charge on there, how much voltage do I need? How much voltage do I need? Well, since I don't have a battery to tell me, I have to talk about the voltage that's going on within the capacitor itself. What's going on inside the capacitor itself, inside this parallel plate capacitor. In a realistic parallel plate capacitor, not like this one, this was exaggerated parallel plate capacitor, the distance between the two plates is very, very small. So that you're only dealing with regions which are very close to either plate. So you can treat the plates as being infinite plates of charge. So if I have a charge Q, positive Q on this plate, and negative Q on this plate, I want to look at the electric field between those two. Well, the electric field, so let me draw a view here, where an edge view. So here's one plate, here's the other plate, okay? This one has positive Q on it, and this one has negative Q. Let's look at what happens between the plates. Okay? The electric field from the positive charge is going to point away from the positive plate. So in the middle region, it's going to look like this. I'll put a little plus. This, and then over to the left side here, it's going to be away from the positive plate. Everybody see how that works? So these are the three electric fields created by that positive plate, or the electric field in the three regions. Now remember, that electric field for an infinite plate is the same. It doesn't matter how far. So all these three are the same, and they're equal to sigma over 2 epsilon naught. So they're equal in magnitude to sigma over 2 epsilon naught, and they point in the direction shown. Now watch what happens when I take into account the negative plate. The direction of the electric field of the negative plate is going to point toward it. Wherever it is, it's going to point toward it. So on this side, it's going to point to the right. And on this side, it's going to point to the left. Now the thing is these two plates have the same area. These two plates also have the same charge on them. So those sigmas are going to be the same. So this magnitude here is also sigma over 2 epsilon naught. Notice what happens outside of the region between the plates. What happens?
Cancel out.
It cancels out. That's a good thing. That's a nice design. You don't want some plates to store electric field that if you walk that kind of goes all over the place, because if I had a capacitor over here, let's say I had a giant capacitor over here, and the electric field for that capacitor kind of spilled out all over the place. Well, if I walk toward to take up the capacitor, I get in the electric field. That's not what you want to happen. You want it to be where the electric field is pretty much contained between those plates. There's a little bit of edge stuff going on because they're not infinite plates. But for the most part, you got it. You've got it nice and stored in here. So out here, the electric field is 0. The total electric field is 0. And in between, they add up. And so the total electric field that you get in between is sigma over epsilon naught. And it's what we call a uniform electric field. So if you want to know, when we talk about creating uniform electric fields, that's how you do it. That's how you create uniform electric fields. Okay, so that's the electric field. Now I want to talk about voltage. I want to talk about voltage and how it relates to the electric field. Let's take a look at the fancy formula first. VB minus VA equals minus integral A to B of E dot dl. Well, the only thing I really care about here, first of all, is the magnitude of the voltage. When I talk about a voltage that's across a capacitor, okay, and I just say VAB like the textbook did, we're not worried about the sign. We're not worried about the sign. Here's my integral. Well, E is uniform. It's going to come out of here. and I'm just integrating over this DL. So all I'm going to get is the simplified formula where this is the electric field multiplied by the distance. So the electric field, so if we look at this other one, this electric field is the voltage across the plates, delta V over delta X, I guess it was, or delta S. In this case, it just turns out to be that the electric field is equal to VAB divided by the distance D. Or that my VAB that I'm looking for in that formula up there is equal to the electric field times the distance D. This is why parallel plate capacitors are kind of, the simplest way of doing it. You've got a nice uniform electric field. You don't have to worry about integrating anything. You just get it. There it is. All right, now. Well, now we can just kind of put all this together, okay? So my electric field is, so my VAB is equal to sigma over epsilon naught multiplied by D. The sigma is what? Charge per area. So that relates to my Q. So this is Q D over epsilon naught A. That's putting Q over A in for my sigma. And then finally, my capacitance is equal to Q divided by QD over epsilon naught A. Now my 100B students, don't tell me what to do, so you guys can too. What do I do with that?
Q's cancel out.
Well, yeah, they cancel out, but I don't like the fraction under the fraction thing.
The epsilon naught.
You invert and multiply. Yeah. And by the way, yes, the Q's will cancel. And they better cancel out because this capacitance, the ability to store charge, shouldn't depend on how much charge I'm storing. Okay? So what you end up getting is that this is epsilon naught A over D. And so that's the formula for capacitance of a parallel plate capacitor. Oh, go back down a little bit?
Yeah.
So you can grab the rest of this? This derivation is actually in the textbook. Yes?
A is the area
Of the plate. And D is the distance between them. D is the distance between the plates. And epsilon naught is that constant. So now if I were to look at this, to calculate a capacitance, okay? Let's say that if you want to be generous with your distances, right? Say let's be generous and say we can get it really close together. So where the distance is on the order of 10 to the negative fifth meters. That's about 10 micrometers there. So if you've ever heard of micrometers or micrometers, it's very, very close together. Okay. The area of your plates to be just anything reasonably sized are probably going to be on the order of 10 to the negative 2 meters squared. Actually, probably less than that. Actually, probably on the order of 10 to the negative 3. I'm being nice here. Okay, a meter square is a huge thing. Take 100th of that, you still got a huge thing. So I'm being very generous of this, just to show you a point. Yes?
Is that negative fifth or negative sixth?
Negative fifth there and negative 2 there. Okay? Now there are ways you can make it so that they're closer together or larger area, but most capacitors are kind of rolled up, if you will, to try to make it so that the area is larger. And there are other designs. But for this case here, if you notice what happens, this epsilon naught term here, 8.85 times 10 to the negative, anybody remember? 12. That's what that is. about 10 to the negative 11. So even with this large area and a small distance in terms of what you think of as any kind of everyday thing that you try to make, you're still going to get something that's order of 10 to the negative 9 nano. Okay? The units of capacitance are called Faradays or farads. Symbolized by a capital F. So a 1 farad capacitor is a rare thing. And if you do see one, there are some 1 farad capacitors that they make for basically instructional purposes only. Just instructional purposes so that students can have nice numbers to work with. Okay, most farads, most capacitors that you work with are in the order of microfarads or nanofarads or even picofarads. Pico being 10 to the negative 12th. Okay, so most of those things that you work with are going to be very small. Okay, they don't make them large, but sometimes we do just have it. If you do, what happens is that there's a material you put in there in between the plates, and we'll go over that in a bit. There's materials you can put to increase the capacitance. But what happens is that material would break down at very low voltages. The maximum voltage you could run the 1 farad capacitor at, and before it broke down, is 5 volts. So you're not going to be using it in any kind of industrial anything. Just. Sorry. Yes.
So what we're essentially looking for is Newton meters cubed over Coulomb squared. That's what farads are.
No, farads aren't that. That's epsilon naught.
But when we
if you want to break down what farads are, let's use the easier formula to do it. There it is. 1 farad is equal to 1 coulomb per volt. There, that's easy. Use the definition. It turns out to be Newton meters cubed per Coulomb squared. Because there's area up here, you multiply, and then the distance down here. So this unit here gets, you have to multiply by meter squared. You get a meter in the denominator, so it's Newton meter cubed per Coulomb squared, but you're just like, what is that? So Coulomb per volt. Oh, wait a minute, it's the other way. Nobody stopped me. It's okay. There we go. That makes more sense. I was wondering how I got a third factor of coulombs that the Newton meter squared per Coulomb squared, that was units of K, which is 1 over 4 pi epsilon naught. The epsilon naught units are reversed from the K units. All right, now here's another concept which is easier developed with using current instead of capacitance. But your book goes with capacitance first. All right. So I'm going to draw batteries again. Shame on me, for drawing batteries again, right? The way to think of when I'm looking at a circuit and I go from point A to point B, okay? I want to look at do I have a choice or do I not? Let's take a look at a couple ways I can do multiple capacitors. So if I hook up some kind of battery between A and B, okay? And I put C1 up here, and I put a C2 down here. Between points A and B. Now you want to think of wanting to go from point A to point B. So when we talk about the voltages that we're going to be putting on these things, we talk about how we're going to get from point A to point B and what you have to go through to get there. What you have to go through to get there. So in this top case here, if I'm going from point A to point B, I could go through C1 or C2. Through C1 or through C2, then I get to the other side. Okay? Such a circuit where you could go through either circuit element to get from one side to the other is referred to as a parallel circuit. That's a parallel circuit. I'm on a completely different page because I'm going to put the stuff that goes with this below it. And now I'm going to take care of this idea. Now if I want to talk about the voltage from A to B, okay, and I have my C1 and C2. Here, to get from A to B, I have to go through C1. What's the magic word that goes in a minute? And C2. I have to go through both. So this is like conjunction junction, right? Here's your OR, here's your AND. I can't think of a but circuit yet, but you know. So this is AND. If you have to go through both of them, this is referred to as a series circuit. That's referred to as a series circuit. What we want to do is we want to find an equivalent capacitance for each combination. In other words, I want to replace both of these capacitors with a single capacitor and store the same amount of charge. So, what I have is I've got, for my C1, well, that's the voltage on that particular capacitor. There's a charge on that capacitor, and there's a voltage on that capacitor. And so C1 is equal to Q1 over V1. And that's always going to be the way it is. So in other words, when we start writing those subscripts 1, we're talking about the charge just on that capacitor and the voltage just across that capacitor. Down here when we talk about C2, that's going to always be equal to Q2 divided by V2. Then I talk about the overall capacitance of the whole thing. Well, the overall capacitance, the equivalent capacitance, the thing that we're going to be looking for, is going to be equal to the total charge stored divided by the voltage between both A and B, the voltage across the whole thing. Okay? So Q total divided by VAB. So now what we want to do is we want to take a look at, well, how are those charges and voltages related to the overall charges and voltages? Okay, let's take a look at, well, which one do you want to take a look at first? Charge or voltage? Voltage, okay. Voltage, remember, is analogous to climbing a mountain. Did I draw my mountain in here yet? Okay, good. Okay. I'll be drawing it again. Okay? I'd like to use the mountain thing because. So the voltage is analogous to. That's actually later, a couple chapters from now. So stop. 100 B's ahead of you. Isn't that amazing? Actually, they don't have to go through any of the calculus. No wonder they're ahead of you. They go over other stuff later. So. Okay. So mountain. So I got a question. So here's camp A, and here's camp B. Okay. And you're climbing. Okay. So we want to know how high you climbed. If you do this. Or Jeff Probst picked you up in a helicopter and then dropped you off.
Path doesn't matter. It's just a change in elevation.
Yeah. So if you ask who rose farther or who went up farther, neither of them. So the path doesn't matter in terms of the voltage. The voltage between A and B is going to be the same no matter which path you take to get from A to B. Do you see that? It doesn't matter. It's just like remember the potential energy due to gravity? You know, it didn't matter what you did, the change in potential energy was the same. Well, the voltage, remember, deals with the change in potential energy of electricity. And the path you take doesn't matter. The path you take doesn't matter. So even though I didn't get the posted solutions, remember that problem on remember that problem on the practice exam where I did this to you? Because I'm evil? Because I said here, you go in the radius r and you take this semicircular path here. What is the voltage difference between blah blah these 2 points? Well, here, if you start to integrate over that, more power to you. Okay? But hopefully you realize, well, that path is going to have the same voltage difference as that one. Why not just take the straight path right along the electric field, calculate the potential difference, and there you go. Hopefully that would have been a hint to you that I gave you like this much space to do it. Do you notice I gave this much space to do it, but you can't even fit, you know, through all the integration, blah, blah. And I am not about to sit here and prove this. I'm sure it's proving. I'm not proving the data integral. That's crazy. So, of course, now we don't have to deal with that. Now we just have to think, oh, okay, no matter which way I go from A to B, the voltage is going to be the same. So that means this V1 up here, that voltage across that capacitor, well, that's going to be the what? How does that compare to the V2, the voltage across this one?
Same.
It's the same. And then what about the overall? The same. So the voltages in parallel are equal. Voltages in parallel are equal. Because parallel means I have a choice of paths to get from A to B, and any one of those paths is going to have the same voltage difference. Any one of them. So V1 equals V2 equals VAB. That's the way the voltages line up in a parallel circuit. Voltages in parallel are the
Same.
same. Thank you. Now somebody else. Voltages in parallel are the same. Thank you. This side. Voltages in parallel are the same. There we go. Now, let's take a look at the charge. Take a look at the charge story. Remember how the charges go on these plates. I'm assuming that the A is the positive side here. So there's going to be plus charges on this plate. Okay? And then plus charges on this plate. And notice that I have access point A here. I have an access point. That's my access point. So I can get to those charges. I got minus charges on this plate, and I got minus charges on that plate. And notice I can get access to those at point B. Oh. So in other words, I got a plus Q1, and a plus Q2, and a minus Q1, and a minus Q2 down here. So what's the total charge I have access to here? Q1 plus Q2. And what's the total charge I have access to here? Negative Q1 plus Q2. So I would, no, those you cancel out because I'm talking about total charge stored on the capacitor. So when I talk about charge stored on the capacitor, the plus side is equal to the minus side, is equal to the amount of charge you've stored. So how much total charge have I stored?
Q1 plus Q2.
Q1 plus Q2. So in parallel, these capacitors are going to add up. The charges add in parallel. So Q total equals Q1 plus Q2. So now let's take a look at this formula. Q, by using the definition of this, solving for Q, Q total is equal to VAB times C equivalent. Q1 is equal to C1 V1. Q2 is equal to C2 V2. In other words, I rearrange my definition of capacitance to solve for charge. And then just put that in here in this formula for charge. However, all of the voltages are the what?
Same.
So I can divide through by that voltage,
And eliminate them.
and that's it. Then I get a formula for my equivalent capacitance that's equal to this. Yes?
Is Q1 plus Q2 Q total 1 1? Is the Q1, is the Q2 equal to the, on the plates, positive Q2?
Yes.
Negative Q2?
Yes. When you talk about the charge stored on a capacitor, it's the charge is stored like this. Sorry about that. It just, let me try to pull that down when I explain this, because it's important. When we talk about charge stored on a capacitor, I mean, if I talked about the total charge of both plates combined, of course it would always be 0. You see what I mean? That's kind of like, it's not what, you know. But the way we talk about, if I say Q is stored on a capacitor, that means that there's a positive Q on one plate and a negative Q on the other plate. So it's Q that is said to be stored. Positive on one side, negative on the other. Okay? That's the way it's said to be stored on this. Did you have a different question? No. So in other words, when I have positive Q1 plus Q2 on this plate and negative Q1 plus Q2 on that plate, notice that Q1 plus Q2 is what's said to be stored. This is the total. Now C1 plus C2, okay? Which actually kind of makes sense if you think about it, because what you're doing is you're adding areas here. You're adding more space to store charges between my two access points, and so I can store more charge. Yes?
So for C equivalent,
Mm-hmm.
the equivalency is like only for parallel.
This is parallel. I gotta do a whole different thing for series. Gotta do a whole different thing for series. Okay? It'll be similar. Now, the reason why I left this box not completed is because what happened if we had a third one? What would I do?
Add it.
It's just add it on to the end here. There. As many capacitors as you have in parallel, you just add them up to find the equivalent capacitance. Let's get serious. Thank you. That's what I was looking for. Once again, our C1 is equal to Q1 over V1. Our C2 is equal to Q2 over V2. And our C equivalent, the thing we're going to be looking for, is equal to Q total divided by the voltage between points A and B. All right, this time I'm not giving you a choice. I'm looking at the voltage first. Okay? If I go the voltage between A and B, I have to go across V1 and V2. So we're not equal anymore, but what happens? V total is V1 plus V2. Right? I'm looking. Okay. So the V total here is V1 plus V2. In series, voltages add. In other words, I have to climb this set of stairs and then I have to go up this elevator. Okay? The total height is the height of the stairs plus the height of the elevator. So in series, the voltage is that. So I'm going to write down that equation. So V total is equal to V1 plus V2.
V total is VAB.
Oh, sorry, yes, VAB, sorry. Now, since the charge there isn't, how the charges work isn't intuitive. I mean, it might be because you might see this beautiful symmetry in physics. And those of you who see the beautiful symmetry in physics, I could just say it and you would accept it. But I want to take a look at something here. I'm going to blow this diagram up. So here's the big, giant capacitor diagram for you. Here we giant capacitor diagram, giant capacitor diagram, giant capacitor diagram for you. You can see. Go. Okay. Now, here's my point A and my point B. And I put voltage on there, and there's charges that get stored on this thing. Okay? So, I have positive Q1 here and negative Q1 here. Positive Q2 here and negative Q2 here. I want to take a look at the H. In the middle. Remember that these orange lines represent wires and plates. Wires and plates, right? Before I hooked up the battery, what was the total charge on the H? The net charge on that H?
0. Before you connected.
Before I connected it.
0.
Before I connected it, what was it? It would be 0. Because if I don't connect it, there's no net charge, right? This H is not connected electrically to anything. There's no wires leading out of it. That actual piece of H is not connected to the battery at all. So if that H is not connected to the battery at all, where is it going to get an extra charge? Nowhere. It's not. It can't get an extra charge. So therefore, the net charge on the H after the battery is connected must be what? 0. Must be 0. This H has to have 0 net charge. It can't get charges from anywhere. It's not connected to anything. This plate and this plate are, but this is not. Well, that's okay. We got a nice charge here and a plus charge here. And the plate will still have this H will still have a net 0 charge as long as Q1 equals Q2. So that's what happens in a series. So capacitors in a series, the charge is the same. Charge is the same. Q1 must equal Q2. So in series, the charge is the same. And if you take a look at the charge that's stored, okay, since now I'm going to put plus Q, I'm talking about my Q, I'll put a little T for total, okay? Minus Q total, plus Q total, and minus Q total. Now I want to look at how much charge that I've totally stored on this. Well, you might think, and it wouldn't be that bad, right? I've got one capacitor with Q total on it, and I've got another capacitor with Q total on it. So how much would that be? 2Q total. However, I don't have access to that. I only have access to this and that. So basically, I just wipe that out. And notice how much charge I got on there. Q, Q. That's it. So the Q1 equals Q2 and equal to the total charge I have. The Q's are equal. So in series, voltages do what? Add. And the charge? Same. Voltages do what in series? And charges in parallel? Add. Thank you. Tricky. So, in series, Q1 equals Q2 is equal to Q total. I need to solve this for voltage. If I solve it for voltage, I have Q over C. Everybody see that? I have to physically show that to 100B, so please. Just up here and put that down there. Okay, so this is Q total over this equivalent capacitance. This is Q1 over C1. And this is Q2 over C2. But the charges are all the same. So I can divide all those out, and I get 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2. And if I had more, you just add them. Yes.
Is two questions. One is C2 kind of the same thing as C total?
Yes.
And then the second question is that H, the reason why it has a net 0, is it kind of similar to why you get struck by lightning in a car? You don't get struck by lightning? Just your car?
That's a little different. That has to do with more with the fact that the car is metal and you are not, and the car, can be.
I mean, like the car's grounded, but then you're in the middle, so you have like a zero net charge.
You're basically. That's more to do with electric field shielding because the car's metal.
Okay.
Okay. Than this. This is just disconnected from the circuit altogether, so therefore it cannot get charged from anywhere. The car situation is basically that lightning strikes is going through the car and not through you. That we'll get to in next chapter. Okay?
Why can't you put the inverse and then just leave it to the same?
The inverse what?
The inverse of the multiplication. I'm trying to see, for what to do, wouldn't you want it to be just C, not 1 over C?
Here's a problem. Don't worry about it.
For the parallel,
Yes.
how does the charge get distributed?
Oh,
Backwards,
I have Q1 plus Q1 plus Q2 minus Q1 minus Q2, and I have access to all of it.
The Q1 and Q2 are different, right?
Yes.
What makes it so that like C1 gets a certain charge and
Let's find out. That's a good question. Here we go. Let's use simple numbers, right? Okay. 3 farad capacitors up here, and a 2 farad capacitor down here. And I guess I should be really simple about this. Should I be really simple? Yeah, let's be simple. And I put a voltage across from A to B, and the voltage from A to B is 5 volts. There we go. 5 volts. Okay? So first of all, I want to know what is the equivalent capacitance of this and the total charge stored in the circuit. And then I want to break that down to figure out how much charge is on each of those plates. How much charge is on each of those plates. Okay? So, okay, so what kind of circuit is it?
Parallel.
Parallel. So the equivalent capacitance is, I'm just going to write down the answer. It's C1 plus C2, which is 5. 5 farads. There we go. Okay. So then I can figure out what the Q total is. Go back to my definition. So the Q total is equal to C equivalent multiplied by my AB. We'll get to the Q1 plus Q2 in a bit. Okay? C equivalent multiplied by my AB. In other words, once I have the equivalent capacitance, to find out the total charge stored, I multiply that by my VAB. That's why we do this. It's a little less evident here because this is such a simple configuration. So the Q total here is 5 volts times 5 farads, which is 25 coulombs. But that's lots and lots of charge. That's why this is kind of unreasonable, but I want to keep the numbers simple. So my Q total here is 25 coulombs. Now let's break it down. We want to break this thing down. Okay? So I want to figure out now how much is on the 3 farad capacitor and how much is on the 2 farad capacitor. Well, here, because they're in parallel, if I know the voltage of the combination, I know the voltage across each one. So because of that, I know that Q3, I'll just do that for the 3 farad capacitor here, Q3 has to be equal to V3 times C3. The voltage across the 3 farad capacitor is 5 volts because it's equal to the voltage across the whole thing. The capacitance of the 3 farad capacitor is what? 3. Hopefully. So there are 15 coulombs on the 3 farad capacitor. How about the 2 farad capacitor? We can do the same thing. Voltage across the 2 farad capacitor, capacitance of the 2 farad capacitor. Voltage across the 2 farad capacitor, it's a parallel circuit, that voltage is the same. Capacitance of 2 farad capacitor is 2 farads. So how much do we get?
10.
10 coulombs. That's how the charge is distributed. Depends on what the capacitances are. Notice the one with the large capacitance in this case takes the larger amount of charge. Now I do have a question for you. There's a check that I did not calculate. Does that check work? And what is it?
Yeah, to see if the total of the charges we got
To be
the same.
as the total charge. In other words, there's a check here because we said in parallel those charges add. 15 coulombs plus 10 coulombs, 25 coulombs. We got it. Check. Okay? Now let's do the simple series. The simple series circuit. Okay? I'll leave it up to you to do some of the more complicated ones and break it down. Now here's the simple series circuit. Let's in fact use our same let's use our same capacitors that we had before. So we go from A to B. We put our 3 farad capacitor here. Whoops. And our 2 farad capacitor here between A and B. The question here is to find the equivalence capacitance, in other words, the same, and the voltage across the things is 5 volts. Okay? So this is 3 farads and 2 farads as before. Okay? These 5 volts, and we want to do the same thing we did at the top. We want to find the charge and voltage on each one, and we want to find the equivalent capacitance and the total charge stored in the circuit. All right, so let's find the equivalent capacitance. So here we go. Formula is a little more complicated, so I actually have to write it down. I can't do it in my head. 1 over the equivalent capacitance is equal to 1 over 3 plus 1 over 2. Now, when dealing with more complicated numbers, if you have parentheses on your calculators, how many of your calculators have parentheses on them? Okay, parentheses on them. Okay, so what I want you to do is I want everybody to calculate this equivalent capacitance and get a number. Write it down. Calculate this, get a number, write it down. I just want to make sure you don't make mistakes. We have a little bit of time here. I drill this into my 100 students. I really do. Because there's mistakes people make like that. And they're just silly algebra mistakes that people make. And by the way, do not solve this algebraically. Do it on your calculator. And write down the number, commit to the answer. All right, how many of you got 0.833 for the equivalent capacitance? You're wrong.
1.2.
When you solve for this, it's 1 over the equivalent capacitance. You have to flip it back up the upside down. 1.2. Yeah, because when you do this, don't just plug this. Remember to flip the answer over again. The equivalent capacitance here is 1.2. Okay? Now, there's a couple of things I do want to point out here, which is nice. Let's say that the capacitors were the same. They were equal. They were equal capacitance. Because there's a lot of problems in the textbook that will do this to you. They'll say, here's the configuration and these capacitors are equal. These capacitors are equal. What happens? If they're in parallel, and I have capacitance C and a capacitance C, right, the same capacitance, two of them in parallel, what happens to the capacitance?
It would be half of one of them.
Parallel.
Oh, parallel would just
Double.
add them to double.
So it would be doubled. If I put them in series, they get cut in half. If I have 3 in series, then it's a third, etc. The series configuration, and this formula, by the way, ensures that the total capacitance you get from a series circuit is always less than either of the other two. It's always less than either of the other two capacitors. I don't care what they are. I don't care if you have a capacitance of 1 farad and you stick it in series with a 100 farad capacitor. The capacitance you end up getting is going to be less than 1. Because series is always going to lower your capacitance. If I wanted more capacitance, what do?
Parallel.
Put them in parallel. That'll give me more. Okay, so now let's complete the analysis of this. So my Q total here is my C equivalent multiplied by my VAB. And so how much total charge do I have stored in the circuit? 6 what? Coulombs. So I have 6 coulombs stored in this circuit. Hold on. We gotta get there. We gotta get there. Hold your horses. 6 coulombs. Okay? Now, on which capacitor is that 6 coulombs stored?
Equal.
Both. Stored on both. There's 6 coulombs on this one, and there's 6 coulombs on that one. So we can now calculate the voltage across each capacitor. So the voltage across a 3 farad capacitor is equal to the charge on that capacitor divided by the capacitance, which in this case is 6 coulombs divided by 3 farads, which is equal to
2.
I don't do it. I do different.
2 volts. 2 volts. V2 is Q2 over C2. Q2 is also 6 coulombs, divided by this time 2 farads, gives you what?
3.
3 volts. There's a check here. There's a check here. In series, the voltages are supposed to do what? Add. Do they?
Yes.
Yeah, they do. So in series, these voltages add, and do indeed. All right. So, how would do something like this? Right? When you're working with a combination, what you do is you start with the smallest combination and work your way out. Smallest combination. In other words, I'm going to replace this with its equivalent capacitance, then take this one. So let's give some numbers here. So C1, let's say, is 3 farads. C2 is 4 farads. And C3 will be 5 farads. Sounds great to me. Okay, there we go. 3, 4, and 5. All right, so the first thing you do is you say that this is C1 in series with C2 and C3 in parallel. So the first thing you want to do is do this combination first in parallel.
So then treat it as 1.
And then treat it as one capacitor in series with this one. So, and if you're having trouble with this, you can actually redraw the circuit after each step. So I'm going to take a look at 2,3 and I'm going to call it C23. It's parallel. So I say that C23 is equal to C2 plus C3. There it is. And how much is that equal to? 9. 9 farads. So now you can actually redraw this circuit, replacing these two. Whoops. Sorry. Let me. Still have C1. With. That. And now these two are in series. So then I say, all right, 1 over my overall equals 1 over C1 plus 1 over C23. I don't know. 3, 1 over x plus 9, 1 over x equals 1 over x. Yes. Calculator. Manipulation.
Not
All right, so on Wednesday, we're going to start talking about energy and dielectrics.
We have homework on Sunday, right?
Yes, yes, we have homework on this chapter. And by the way, it's chapter 24. Chapter 24.
Flip-flopped, and you'd still be able to learn it just as easily. So The answer to your second question is realistically that's money. Okay? The answer to your third question is pretty good so far. All right? There you go.
Are you saying pretty good so far based on how many tests? Because if it's just two, then
No. I do a problem at a time.
Oh.
And the thing that I do on your test, because I do take into consideration fine, I'll just use the regular word, because I do end up scaling grades at the end of class, end up doing that, is to be consistent. So in other words, if you do a problem and you make the same exact mistake that somebody else over here did, and show the same work that somebody else over here did, then you get the same grade. That's why I need to do it one problem at a time. That way I'm consistent with the grades. That way I don't have to worry about how much points exactly I would take off for something, because people love to debate that. But since I scale, it's like, as long as I'm consistent in the number of points I take off, it works out. And I end up changing that. So if you get one of the first few tests that I grade, you'll notice things get marked out, and I'll put different numbers of points because I shift points around, because I'm thinking so many people are missing this, and people are, you see what I mean? It's just, but I try. It's the way we do. And so that's another reason why it takes me a while. I can't just go in and just flat out grade, because of the fact that I want to make sure that I'm consistent with your all's grades, and that they're fair. And then I scale, which is always something that happens. Unless you guys finishing earlier on this test is an indication of maybe that for some weird miracle that the test averages like 70, whatever, I don't know. It almost never is somewhere.
It's lower than 70?
No, I said the miracle would be if the test did have an average of 70. That's a miracle. Okay, that's.
Maybe just take our hopes and just smash them down to
No, that means if you get a 70, you're well above the curve, so that should take those hopes.
Here we go. So we're going to enter into a section of the text where we stop going over. We're no longer going to be looking at the microscopic so much. The first few chapters were everything was kind of abstract, and what we looked at were microscopic things, abstract charges on some coordinate system, and the electric field that they produced, and the electric field and the forces between two ambiguous charges. That I don't have a ball of charge that I could pick up and show to the class and demonstrate it with another ball of charge. I don't have those things. Don't exist. Okay, we don't have those. So we're going from that to something that is more macroscopic and concrete. These circuits. Okay? Because the things that we're going to be going over now do exist. You will be working with them. Okay? So the first things that we're going over. I'm just doing this to keep myself on track, that's all. Not that that ever really completely works, because my tangents go here. Okay. So, the first thing we're going to go over is capacitance and dielectrics. Oh, yeah, I kind of would do that. Try zooming out. All right, so I'm going to start out with the capacitor. You haven't seen these yet in lab. I don't think so. Not yet. Have you seen any of these yet?
No.
No. Okay, close enough. You'll get them before we. Capacitor is a device that stores charge. And we talk about the simplest form of a capacitor being just two metal objects. And if I connect those two objects to a potential difference, okay? Now, this is why I don't like going over this chapter first. I actually like going over the other chapter first because we talk about the thing that creates the potential difference. So I'm going to briefly segue into that. If we want to create a potential difference between two sides of something, all we need to do is have chemical reactions on either side that have different potentials, i.e., one of these things. Now, there are other ways to do it besides getting a battery, but if we get a battery, we can do that. Okay? And so all we talk about when we talk about a potential difference, this means we're hooking it up to a battery, or we're hooking it up to an outlet, or we're hooking it up to something that is generating a difference in potential and can be the source of charges. And can be a source of charges, for charges to move from one side to another. So if I connect these two to a potential difference, and so this is a capacitor symbol, and sometimes capacitor symbols are also drawn like this. How many of you have seen these symbols for capacitor before? Anybody? One, a couple of you. You electrical engineer people, right? Yeah. This is most capacitors, which are pretty much symmetrical. It doesn't matter which side you connect to what. This side, I would tend to think would have a preference for one or the other, though I don't know. I never used this one. I always used that one. So, because in here, all capacitors that we have or we deal with are symmetrical. It doesn't matter, which side, plus or minus. Okay, so we're going to hook this thing up to a battery, and the battery symbol looks like, well, there's a simple battery symbol which looks like this, and this is the potential difference between two sides. Okay. And the long side is the plus side, and the short side is the minus side. And so we're going to hook this up to a battery, which creates a potential difference, which means the charges can now move onto this plate because of the potential difference. What happens is that there's a net positive charge that moves onto this left plate, and a negative charge which moves onto the right plate. Okay, so we have conductor A and conductor B, okay? And if I took the battery off of here now, if I disconnect the battery, then what we have is if I disconnect the battery and I think of what happens to the charges, well, the charges don't have anywhere to go. These wires here are conducting wires, but the gap in between is some kind of insulating gap. There's a gap in between, and so they can't jump from one side to the other, so they just stay there, i.e., you've stored charge. That works. Yes, see? And by the way, I could take that charge and then use it to temporarily power something else. So the capacitors are devices that store charge. All right, so we define a quantity called capacitance. So in other words, this is A and B. This is point A and B, the two sides of the capacitor here. And what we say is that the capacitance is the amount of charge you can store divided by the amount of voltage you have to put across it. For the remainder of this chapter, we're just going to talk about from A to B, and we're not really going to set up a battery. I'm not going to draw a battery because that's the way your textbook does it. Your textbook won't draw batteries again until the next chapter. Actually, your textbook hasn't drawn a battery yet. Okay? They just say from A to B, this is what's going on. Okay? I'm trying to be a little more practical and say, well, you need something. Let's just put a battery for now. I could do it with other things, but with batteries. Okay, so that's our, there it is. There you go. So this is our basic definition of capacitance. Basic definition of capacitance. Okay? Sure I'm not skipping anything. Okay. So now we're going to look at the simplest geometry. The simplest geometry, which, by the way, will look like this, okay, is what we call the parallel plate capacitor. Parallel plate capacitor. Parallel plate capacitors, you have two plates that are parallel to each other. With area A, so that's the area of each capacitor, and they're separated by some distance D. They're separated by a distance D.